Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. We are now continuing through logarithmic functions as a review for college algebra students. You, again, just to reiterate, should have seen logarithmic functions in your Algebra 2 course. So this is more of a high-level review, kind of a quick review, and we kind of barrel through these sections. Not that I'm trying to rush, it's just otherwise I'm just teaching you Algebra 2, and you already have credit for that, so why teach that? You can always look through my previous videos for my Algebra 1 and Algebra 2 students if you feel as though you need to review that on a fundamental level. It's perfectly fine. It's just not usually the purview of a college algebra course to review that much. All right, in this video, we're going to spend time on probably one of the most important parts of logarithmic functions, and that is finding the domain of a logarithmic function. Recall, the domain of a logarithmic function is all positive real numbers. In other words, the argument of this logarithmic function must be positive. It can't be zero and it cannot be negative. That being said, the rest of this video is just going to be focused on finding domains of logarithmic functions. For an example, find the domain of this logarithmic function. Remember, we require that the argument that I'm highlighting here has to be positive. Luckily, it's going to be, actually, because it's a square root in the numerator and a square root in the denominator, both of which will always return positive numbers. However, the radicands, the stuff underneath these square roots there, have domain restrictions in and of themselves. So let's go ahead and fiddle with this a little bit and approach it how I would recommend approaching it. First thing I would note here is that we require the square root of 2 minus x divided by the square root of x plus 3 to be greater than 0. We completely require that. Now, again, I just want to state, these are square roots. They're only going to return positive values. So for the most part, well, I should say they're only going to return positive or zero values. So for the most part, this inequality will be satisfied as long as x can be plugged into those radicals. So we have to figure out, what can x be within those radicals? So all of a sudden, our question about what is the domain of the logarithm becomes more about what can you plug into those radicals. But it's still the same question you're going to face every single time when you are asked for the domain of a logarithm. You're going to say, I need that argument to be positive. So I start there. And then I say, okay, well, let's talk about these other things like 2 minus x. I know if it's underneath the square root, it has to be greater than or equal to 0. However, we don't want it to actually equal 0, because if it equals 0, then the numerator of this guy right here is going to be 0. And that's a problem because we want that fraction to be strictly positive. So I am going to force this to be strictly greater than 0. Again, because 1, it's underneath the square root, and 2, I can't allow it to be 0 because then I'd have 0, and I need that left-hand side to be strictly greater than 0. So this leads to our first set of conditions on x, that if you add x to both sides, x must be less than 2. So that I'm going to highlight that as our first set of conditions. I know for that numerator to work, I need x to be less than 2. For that denominator to work, well, we also require that x plus 3 is, again, strictly greater than 0 for a completely different reason, actually. We require it to be strictly greater than 0 because, 1, it has to be positive because it's in a radical, a square root. And 2, it can't be 0 because if it were, we'd be dividing by 0. So that's a problem. Great. So if you subtract 3 from both sides, you get that x must be greater than a negative 3. So we simultaneously need x to be less than 2 and greater than negative 3. If you were to graph this on a number line, it would look like the following. I'm just going to graph this out. Here's negative 3 right here, and here's positive 2 right there. I need to highlight all x values that are simultaneously less than 2, but greater than negative 3. I'm not going to include those edges, so I'll put a little parenthesis there and a parenthesis there. I'm not including those edges. And that yellow highlighted region gives me my inequality. In other words, gives me my interval over which I can use x values from so that I get a positive or a workable argument for that logarithm. So the domain of that logarithm would be all x values in the interval negative 3 to positive 2, not including the endpoints, because they would cause either division by 0 or they cause the fraction or the argument of this logarithm to actually be 0. So that's a kind of a starter example, and it doesn't super illustrate the domain restriction on the log, but it still does allow us to see how you would approach these questions. You're just going to start with the stuff that I highlighted has to be positive. Now this one is much more traditional. We have g of x is equal to the natural log of x squared plus x minus 6, and we're asked to find the domain of that function. Again, I'll highlight the argument. This argument right here has to be positive. So we require x squared plus x minus 6 to be strictly greater than 0. And if you haven't seen my videos on solving quadratic inequalities or polynomial inequalities, I solve these always by graphing if I can. This, we'll see if we can factor it first. So let me just go ahead and see if this factors. Looks like it'll be a plus 3 and a minus 2. And this allows me to take a look at the graph of y equals x squared plus x minus 6. So I'll just quickly graph that. We have zeros at 2 and at negative 3. And we know that because our quadratic has a leading coefficient that is positive, that this parabola will open up. So I know that our parabola looks something, not exactly, but something like the following. Just kind of chicken scratching it out. It looks something like that. Nobody asked me to graph this, but I like to solve inequalities by graphing. I should probably label that so you know what I've just done. This is y equals x squared plus x minus 6. And we're asking, when is that parabola above the x-axis? Well, you can see all these x values that I'm highlighting here and actually over here, they lead to function values above the x-axis. All of those highlighted x values do that. And so this means that our parabola is greater than 0 for all those x values I've highlighted, from negative infinity all the way up to negative 3, not including negative 3, and everything from 2 to infinity, again, not including 2, and you never include infinities. Infinities you can't grab onto, so you would never include those. So finding the domain of this function is actually as easy as just graphing a parabola. Our domain is all x values in the interval negative infinity all the way up to negative 3, union with the interval starting at 2 and climbing to positive infinity. And that's it. So finding the domain of a logarithmic function is incredibly important as we move through mathematics, and I just want to provide you with the ability to easily do that. All you're doing is solving inequalities, and that's why you learned how to solve inequalities in our previous videos. If you haven't watched those, there is a video and it's titled Linear Inequalities and Absolute Values, or maybe Solving Absolute Value Inequalities, but I think I solve inequalities in there as well. And I just did a quick search through all my college algebra videos, and I realize now, actually, we haven't even talked about that. So it's a good thing that I did this in this example. So let me reiterate what I did then, because that is kind of critically important. If asked to determine when an argument is greater than 0, it's obviously an inequality. It's when is that greater than 0? So it's an inequality. And really, graphically, all it's asking is, when is that graph of that parabola above the x-axis? So the easiest way to solve a quadratic inequality like this, or actually pretty much any other inequality as well, is to graph it and find out when it's above that x-axis. So I graphed it by finding the x-intercepts first, so I factored it to find the zeros of that polynomial. And then I went ahead and graphed it. I knew it opened up because, well, lead coefficient's positive. And then wherever the graph was above the x-axis, those x-value regions, those highlighted x-value regions right here, and also right over here, those are my solutions where I can easily tell somebody, yep, my parabola is above the x-axis in those regions. So I guess I sort of snuck a lecture in on you here, but that's perfectly fine. This is a great way to solve inequalities. Just graph them. Very nice. Now, a lot of people don't like to do that. They like to use sign charts. You're more than welcome to use sign charts. However, I personally find that sign charts a little bit too algorithmic, and they don't lead to better graphing skills. And to be very honest with you, all of us need to have better graphing skills. So it's better to practice solving inequalities via graphing.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.